I'll start maybe slower and then accelerate as we get into this course. Firstly, my name is Onn Shehory, and I've been some time to the Asian community, so I've been teaching several courses in such schools, and of course attending almost every EASSS since it was initiated. So I do have some background that I would like to share with you, and I hope as a result of this course or lecture or tutorial, whatever you choose to call it, you'll get some new insights into non-cooperative games and auctions. I know that there was a course on cooperative games yesterday. Maybe some of you have attended. Those who have attended the cooperative games, can you please raise your hand? Okay. So we have a majority, but not everyone. So I'll take this into account. So game theory has two major types of games it handles. One of them would be cooperative games, and the other one is non-cooperative games. Actually, I was studying both. And initially, my plan was to give a lecture on cooperative games in this summer school, but then someone else, which I know very well, decided they would like to do it as well, so I was moving to non-cooperative games, and this is a type of cooperation, as you can tell. So I'll give this course on non-cooperative games and auctions. I've done some both theoretical and practical work on auctions, so I'll try to share with you and let you understand what it's all about. There would actually be another course, I think, tomorrow on mechanism design. Maybe some of you would also participate, which is actually, in a way, continuation of this whole topic of games. Because mechanisms, once they are designed, they are a type of a game, and the design of those is actually a process in which you design a game, if you would like, and allow agents to take part in it. So let's start this way with a game. Actually, this is a cooperative game, not a non-cooperative game. It's called the glove game. It's well known in the art. And what you see here, a game where you have three players, 1, 2, and 3, there are the names. And 1 and 2 have a right-hand glove. Number 3 has left-hand gloves. And of course, each single glove has little value, but once you pair them up, they have much more value. And these guys would like to sell those pairs. The only way to sell those pairs is to cooperate, to get into groups, and the groups which are possible are either 1 and 2, or 2 and 3, or 1, 2, 3 together. 1 and 3. So 1 and 3, 2 and 3, or 1, 2, 3 together. Of course, every such group is illegal and provides some profit, and there is a need to decide which one would actually form. And this is not the only question that we have here. Firstly, we need to decide which one would form, one question. Another one would be, okay, once we have, how do we allow people or agents to actually go through this formation? It's not just about, okay, I know that it's 1, 2, 3. How do I actually come to this decision? How do I, as an agent, participate in this? So we need some, if you would like, algorithm or mechanism that would allow to support this process. And once we have formed this, of course, how do we divide the profit? So do we split equally? Suppose we have 1 and 3 cooperating, we can do half and half between 1 and 3. If we have 1, 2, 3 cooperating, do we have a third to each? Do we have half to number 3 and quarter to 1 and 2 because they kind of less powerful? Does number 3 take all? It depends on many assumptions and rules that you apply, and you need to design this in advance. So in fact, it's not that simple to know what to do here. And in fact, you need to come in advance with some assumptions or some rules or some preferences of yours as a designer to decide what you want to achieve. Do you want to achieve fairness? Maybe. That's fine. Actually, I would prefer fairness if possible. But what's fair here? If two guys bring a right-hand glove, is it fair to provide them a third of the profit, or should they get less? Fairness for itself is not well defined. And in fact, if you go to the extreme, if you play the actually if you measure the power of the players, player 3 is the most powerful, because if that guy does not participate, no one can get anything. He can always say, you know, to 1 or to 2. If you do not give me all of the money, I'll go with the other guy. And players 1 and 2 cannot say that. So conceptually, if you go to the extreme, player 3 gets everything. Okay? Which is also one way of solving this problem and coming up with a mechanism that would fit that. So this gives you one example. We'll go to another example before we go to the details. So an auction, an English auction, I assume everyone does know that, but just in case you don't, it's a case where you have an item, usually a single item, which is placed for sale. You want to sell it, you want to maximize as an auctioneer, you want to maximize the price of the item sold. Okay, so what do? You allow players to bid, and they actually increase and increase and increase until no one further increases the bid, and the highest bid wins and pays the bid and gets the item. A simple protocol, yet it's a protocol. You have very, very clear rules of what's allowed and what's not allowed. This is a case of a non-cooperative game because, in fact, the players don't even need to know about one another. They just place the bid, and they try to maximize their own benefit by getting the good that they want to get, the item they want to get, and get it for the lowest price that they can, given the behavior of the others. Okay? So this is an English auction. Another example, this case is non-cooperative. The previous case was cooperative because to do something useful, you had to work with others. This case, the auction case, is non-cooperative because to do something useful, you need to do nothing with the others, and actually you are in competition with the others. Okay? So far, we've seen 2 examples. And this is the list of issues that I intend to speak about today. And the examples were just to give you a flavor. So we'll speak about protocol strategies, we'll speak about attitudes of players and agents, about rationality, about stability or equilibrium if you would like. I'll revisit Nash, assuming that some of you have seen it before. We'll look slightly at mechanism design, maybe even skip that because this will be spoken about in another tutorial, but maybe just touch on it to say what it's all about, and those who are interested can actually attend the course tomorrow. And we'll speak about auctions, and both in the theoretical aspect, and I'll bring some examples of auctions. Actually, I was involved in actual business auctions where actual services were auctioned or products of auctions, and I'll show you how it was going on, what was done there, what were the results of behaviors of players, and so on. In fact, auctions in theory and in practice have much similarities because it's some type of mechanism which is rather easy to implement. So this is about the outline, but what I'd like to say is that my style of delivering courses is that I do have my presentation and I do deviate from that. So it's not that I always follow the slides. Sometimes I skip some of them, and in many cases I add much more content which is not there. So it's not that you read the slides and you know what I was saying. I mean, you can follow based on the slides, it's okay. And I do follow them in general, but I do deviate here and there. And I do some activities in which you must, it's not a must, but I prefer that you be involved to give you some feeling of how things actually are actually built or taking place, or how processes are going on, and so on. I assume, but I'm not sure about that you do have with you some piece of paper, some pen or pencil, if you need to write something. Not homework, don't worry. And just maybe write some 2-3 numbers and maybe compute, calculate something which takes you, 1 or 2 variable equation. No integration needed, no derivation needed, just very simple math. don't worry, it's not something difficult. I think it would actually be interesting for you, but if you have the ability, the capability to write something, it would be very useful. And I'll correct your assignment at the end of the class. Don't worry, just kidding. Okay, so let's go to the EASSS. We have here, we're speaking of mechanisms, and mechanisms are actually something, or protocols if you would like, because it's, what is it all about? You have a set of rules. Actually, that's about it. Usually I like to use as an example the chess game, because most of us know the game, not necessarily playing it, but we know the game. There are strict rules of what you can and what you are allowed to do and what you are not allowed to do. If you have a pawn, you can only move the pawn in very strict ways. You cannot do whatever you want. You cannot take it from here and put it there. It's not a legal move. So you have those moves which are allowed and other things which are not allowed. These are the rules of the game. In fact, it's in a sense, it's a mechanism. You have two players, each one. So the rules are that each player at his turn has the right to move one piece, and the piece chosen must be moved based on some specific rules, and that's about it. So you have rules of behavior within the protocol. Now the players must follow them as long as they participate. Of course, a player may decide, you know what, I'm moving this pawn to that corner, although I'm not allowed to. This is possible, but then you're likely out of the game. You cannot participate, you cannot be part of the protocol once you break the rules. Okay? So protocols are actually those rules that tells you exactly what you need to do if you participate. That's it. But they don't don't tell you everything. They just tell you what are the rules. You still have some freedom, which we'll discuss shortly. Example, an auction is a protocol. It tells you exactly what you are allowed to do and what you can do. An English auction tells you what bids are, what you can do, what bids are possible. So for example, if the current bid at the auction is 100, you cannot now bid 80 because it's lower than 100. You must bid for more than 100. So this is the rule of the game. This is a rule of the protocol. Even negotiation is in a way some type of protocol, because in many types of negotiation there are rules of what you can and what you cannot do. Suppose you negotiate the price of some item in an open market. The common practice is that once you have arrived at close to an agreement price, so suppose the seller is asking for 100 and you want to pay 20, and he says, okay, I'll give you for 80. You say, okay, I'll give you a 50. And then you get to, he says 70 and you say 60, you're just 10 units apart. And then you say, you know what, I said 50, but now it's 20 again. It's possible, but in most markets it would be kind of unacceptable to do that. Although I've seen that done in the past. And people break the rules sometimes, in particular humans which do not tend to follow all of the rules. Okay? But the unwritten protocol of such negotiation, open market negotiation, is that when you get closer, you don't retract to a lower price again, or the seller does not go back to a higher price, unless something extreme happens, some unacceptable behavior. So then both sides can move back to original or even more extreme stance. So I'm saying that you have this protocol, you have these rules. Negotiation is also a protocol. Voting is a protocol because there are many different ways of voting. Some voting is a majority voting. Some voting you have, for example, if you have a tie, there may be a case where someone would have the ability to have 2 votes. It's a different protocol. It's not everyone has the same vote. There are some votings in which, to start with, some players, some voters have more power than others. This is just a specific protocol of that type of voting. So not all voting mechanisms are democratic, so-called. They are voting, but they're not necessarily democratic, or equally assigning equal power to all players. But what do we want to have once we have protocols? We want them to be such that would, if possible, maximize the profits of those who participate in the protocol. This is desirable. For not always can you do it, but you want to have it. You also want to have protocols which would be difficult or impossible to manipulate. For example, if we do voting, so in voting systems, actually in democracies, you do find cases where some candidates bribe people to get them vote for them. This happens in many democracies. It's not something unique to a single democracy. It does not happen in all democracies, but you do find such cases across the world. It's not a single country in the world where the election is running, and eventually found out that the vote does not fit what the statistic was saying, and then he was saying, okay, what happened? And some investigation, in some cases, finds out. Some cases are not even revealed, but in some cases, you find out that some guy was bribing people or paying a whole town in some way to vote for him or for her. Of course, it's not nice, it's immoral, but it's done. Which means that the regular election voting protocol is subject to manipulation. You can do things out of the protocol which would change the result of the protocol. Okay? So by this I mean that this is not a case where you can enforce. You can, after a month, after the month, punish those that have done it if you reveal that. I assume that because revealing such cases is also costly, not always do you find out that such things have actually happened. Sometimes you do, sometimes you don't, which means that those that do it have some non-negative, they have some probability to succeed as a result of this. Because maybe you would find out, and then they would be punished, and maybe you won't, and then they would be elected and get to power based on paying money to some people, which is not desirable, but it's a protocol which is not enforceable. Okay? And you would like to have such a protocol which are enforceable, which are difficult or preferably impossible to manipulate. Indeed, there are such protocols, not for voting maybe, or not for simple election voting, but there are some protocols which actually motivate the participants to behave truthfully. Not only that, you can actually design protocols to be this way. Not always is it easy, not always the protocol would be a simple one, but it's possible. I believe that tomorrow in the mechanism design you would see such cases more than even one. The common term is incentive compatible, which means that you incentivize the players to be compatible with the protocol. But for us as computer scientists who implement things eventually, we also want protocols to be, in a way, simple or easy to implement. Because if it's complex, firstly, it may be computationally heavy, which is not good. In addition, it will be difficult to write the code, which is also not good. And suppose we have actually implemented it, chances are, if it's complex, either people don't understand it, or it's subject to multiple bugs, or both, actually. So either way, it's not something which is positive. We want to have something simple. This is one of the reasons you see auctions so commonly used, because they are simple protocols. It's very easy to implement. In fact, I would not direct you to a specific website, but if you go to the web, if you wanted to start up an online auction, you go to the web, you have so many sites that offer you free of charge software that would help you build an auction website. And this is there for 15 years on the web. So auctions which can be put online, I'm not sure about 15, I think it's 14, but it's not 5. Anyway, I remember, I recall from the year of 2000, but I am not sure that in 1999 there was something available for free in the internet. Anyway, the year 2000 I've seen at least one site which gave you for free software for putting up an auction. And today you have so many of them, you want to have one. And if you want to write some by yourself, it's also not difficult. Students of mine have written such auctions by themselves many times, and it was not, it's not a huge project. It's you need to write some. You have, I think, a few hundred lines of code if you want to have it simple. If you want something fancy, you would need more than that. But it's not something which is prohibitive. You can do it, and We are computer scientists, we're not afraid of writing some code, I assume. Anyway, this was quite in length about protocols. Now about strategies going into chess. In chess, the ability to be a winner, to win the game, depends not only on the rules, in fact mainly on the strategies that you apply. If you apply good strategies better than those that are applied by your opponent, chances are that you would win the game. And in fact, the protocol tells you what are the rules, but it does not tell you what to do exactly at each turn. It doesn't tell you whether you should move the queen or the king or the bishop. It doesn't tell you which one and where to move them. It tells you what you are allowed to do, but not what you have to do. And your decision of what you have to do is based on some strategy, which may be very complex to compute, but there is a strategy. And the strategy is actually the set of behaviors available for a player. It may be a small set, and it may be a very large set. So this is not dictated by the protocol. In most cases, the protocol actually doesn't tell you what the strategies are. It's your decision, it's your local computation based on your local information, and you make the decision about it. In an auction, for example, suppose you have an auction, likely you would like to bid the smallest bid that you can, which would be taking the current bid and adding the minimum addition that you're allowed to. If it's, suppose the price is currently 100 and the step is $1, so you would bid 101 and not 110, because 110 is nothing of value, because you may be losing $9 or euros or whatever coin you have for nothing, because 101 is better for you than 110. Of course, there are cases that in which you would like to increase the bid more than just the minimal step for other reasons. We'll discuss this later maybe, but you may want to say, I want to affect psychologically the others, tell them, I'm determined to get this item, don't even try to compete against me. I'll put the current price is 100, I'll put 200. For me it's still beneficial, and I'll know that if I show you that I'm so much eager to get this item, you wouldn't participate anymore. This is a psychological effect, which is one type of strategy, of course. I think it's not a rational strategy, because you can get to this 200 even gradually, if you would like to. And maybe you would stop at 150, so why spend another 50 for nothing? But some people do that, and in fact, because an auction involves people and not just rational agents, so in some cases, such strategies actually work for you. You are able to affect others by communicating in some way that you are going to buy that no matter what. In fact, it reminds me of some auctions that I've seen a few years ago. I was watching an online auction for some product, for some gadget, and the players were so eager to get the item that eventually the winner bought it for more than, actually 50% more than market price. Which was ridiculous, You can go to the store and get it for 100 and you bought it for 150. Why do you do that? So this is an example of an irrational behavior. And during the competition, because that guy was, two guys actually were competing, they wanted to show one another they are stronger in the auction. It was very costly for them. Those 50 were just to show off, I'm stronger, I'll win. Whatever, I'll win this, as a rational person, I'm saying, makes no sense. But some people are actually getting involved, and those psychological or sociological effects are very strong in such cases. In fact, that's the reason most of the auctions, the online auctions, are actually English auctions or something similar to English auction, because in those cases, you actually see what others are doing, and it affects your behavior. Not everyone's behavior, but enough players are affected to make the price go up. Actually, it becomes higher than it would have been in a rational case. most cases are not above market price, but they're actually favoring the auctioneer because of those psychological effects. If it would have been a sealed bid auction where you don't see what others are doing, you would just put your price and that's it. You don't see the others. And you end up either winning or losing, but you don't get any psychological effect of what the others are doing, and I should compensate, or maybe I'm wrong about my behavior, I should have a higher bid as a result of others doing something of this type. We'll discuss this when we discuss some strategies within auctions later on. Should have turned off Skype, but now it's not the right time to turn off. So once in a while you'll see my colleagues appearing online. Anyway, so in similarity to protocols, we want strategies to be such that would allow the players that play them to maximize their profits, their payoff. And we'd like it, again, to be, if possible at all, impossible to manipulate against. And of course, I'm saying if possible at all because in most cases it's not possible. If it's possible, maybe it's computationally too complex to find out which ones are those that actually impossible to manipulate against. And this brings us to the point that we want it to be feasible, computationally feasible, which is something important when we speak about real systems, real agents. One thing we should keep in mind that strategies in many cases depend on the strategies of other players. The auction case was an example, but in chess it's also an example. My strategy depends on what you do in most cases. I don't just do my moves regardless of what you do. I take into account your moves and then I respond. Even if I play in advance, I play in advance based on what I assume you would do. Okay? So I need to take this into account when I plan strategies, and when I plan agents that behave strategically, I need to compute things taking into account the others. One thing which is affecting games in general, both cooperative and non-cooperative games, is the fact that agents may be either self-interested or benevolent or something in between. Self-interested, that is, they prefer to maximize their own payoff regardless of what happens to the others. Benevolent agents are those that actually prefer to maximize or to help others maximize their, not the benevolent, but the other agents' payoffs, and in many cases maximizing the social welfare regardless of whether they get more or not. They will be benevolent. In many cases, we have agents which are somewhat in between. They try to give themselves enough, but also help others to get to good shape. This is actually typical to humans. Humans are usually not extreme self-interested and not extreme altruist or benevolent people or agents, if you like. So you have the whole spectrum, and in fact, humans actually change attitudes based on context in many cases. But we need to take into account the fact that agents can be either case, and when we design or when we look at a game or a protocol, we need to think, are the agents self-interested, are they not? And how does it affect the specific mechanism? We also have something which is affecting behavior in games and also affecting the protocols is the risk attitude. So some players may be risk prone. They actually prefer risk over other things. This not just prefer risk for the sake of risk, but by taking a risk, you may gain, you may increase your gains. Some agents are the opposite. They're actually risk averse. They hate risks. They want to have some guarantees, actually high guarantees if possible, that they get some specific payoff or goods. And some agents can be risk neutral. In fact, the risk neutral case is maybe perceived as more rational in the sense that it maximizes the expected utility or the expected payoff, because it ignores risk. It's, for an edge which is risk neutral, the case is that regardless of risk, the risk represents actually a case where I may take a higher risk, but I reduce my probability of getting the payoff, for example. Actually, we'll take an example very shortly, so then we'll see the trade-offs that we can get here. In any case, humans are almost never uniform in their risk attitude. Usually their risk attitude depends on many aspects which are, if it's money, the sum may change your attitude. If it's other utilities, you may sometimes be risk-prone, sometimes risk-averse, sometimes neutral. So humans are not uniform, and it really depends on context. And we'll see an example shortly. Here it is, example. So suppose you need to choose. You have two options, okay? You can get either €1,000 right now, cash, or you can get a lottery, which tells you, it has a 10% chance to win €10,000. Now, if you know how you compute expected utility, the expected utility is equal in both cases, because the expected utility is a chance, or the probability, times the value. So in the first case, you have a chance of 100% times 1,000, so the expected utility is 1,000. And in the second case, you have an expected utility of 10% times 10,000, which is again 1,000. So the expected utility of both cases is the same, 1,000. Okay? So if you are completely risk neutral, you don't mind. Both cases are the same. But if I'm asking you, you have these two options. What do you prefer? Should you take option 1 or option 2? 1. Who favors 1? Okay. The vast majority prefers 1. Who prefers 2? Okay. So a few would prefer 2. And now it's the same value, expected value. Some of you prefer this, some of you prefer that. Actually, if you were completely risk neutral and rational, you wouldn't prefer any of them. You would say, okay, whatever. They're the same. But here, getting €1,000 cash is something that you are guaranteed to have your cash. It's very useful. You can use it right away. And getting 10,000, which is much better than 1,000, is only a 10% chance. If I don't get it, I get nothing. So it's quite understandable that many prefer to in such a case to be risk averse, avoid the risk, and have a guarantee of having this 1,000. But this is because of those specific sums and of what you see, the utility you see in using those €1,000. In case it would have been, for example, a 10 and 100, I think the results would be different. Suppose instead of 1,000, you have €10 for sure, or €100 with a 10% chance. What would you vote in such a case? Option, who prefers the 100 for 10% chance? That's what I thought would be. I mean, more people would. Okay, for just getting just a 10. Okay, I can use it, but it's not that useful. But getting 100, which is just 10% chance, is much more useful. So I prefer to take a chance. And so you see, the context was actually changing. The same chances, different sums was a big difference. Same chances. The expected utility in both cases, in the first case, was both cases the same. In the second case, both options the same. So in fact, you see this diversity. But now let's see what happens if we change in the first case of the 1,000 and 10,000, the other sum, for the 10,000, get a 20% chance of winning. Okay. Now the expected utility of the second option is higher. It's 2,000. It's higher than the expected utility of the first one. What would you do then? If you are rational and risk neutral, you should definitely prefer the second option. But you're not. So likely some of you would still prefer the first option. Think of it for a few seconds. Would you prefer the first option? Okay. Second option? Okay, so you are somewhat rational. Well, you know, none of us is rational. So don't. It's not, you know, saying that rational is not a preferable trait. It's something which is useful in some cases. In some cases, as humans, it's not useful. You know, I would follow the same policy as you did in the case of equal chance. In the case of unequal chance, I'm not sure. Likely, I would do like the majority here, would prefer the expected utility of 2,000. But we are not completely rational, and you know, it's fine. It's good. In fact, it's good. You know, for me, having 1,000 cash is more useful than having a lottery. I don't know what will be the result of the lottery. I know that the expected utility is such and such, but I don't know what I'll get. So I completely, in fact, some theorists actually say about game theory that the way in which utility is computed is not the right way. So if I just compare the expected utility based on the value times the probability, I'm doing something wrong. And that's the reason we do not actually, for this, we actually do not model correctly the utility of humans. And humans are rational. You know, this is a philosophical discussion because I don't mind whether we are called rational or not. We behave by some rules which are different from the classical theory of rationality, but I think this is not an issue. This is actually a nice thing about human beings in difference from machines. Anyway, let's proceed. Speaking of rationality. So rationality, I think you already understand, is the case of, is a behavior which prefers more over less. This is a simple description. Preferring more over less is a rational behavior, and the rational player which has a whole set of alternatives should always prefer the alternative which provides the highest payoff, or the highest expected payoff. Of course, the problem with rationality is that in practice, when you look at real daily cases, you cannot compute all of the alternatives. It may be infinite, or just very large. And in such case, you cannot compute all of the alternatives just because you don't have the resources to compute them. So you cannot actually know all of the alternatives, and you cannot be rational for this reason. In some cases, you don't even have any algorithm that can compute that. So it's even if you have the resources, you cannot compute. Commonly in the art, it's the way to fight that was to have what is called bounded rationality. Rationality which is bounded by in the sense that it actually looks only at a subset of the alternatives by maybe limiting the time for computation, or pruning the search space of options, or many other restrictions that would actually make you compute less and finish fast your computation. And as a result, you can do it feasibly, so you can do it. It may be too restrictive in some cases, and of course, strategically it's inferior to rational because you compute less, you may be missing some of the important alternatives here. In some cases, we even go farther, we do some type of good enough behavior. I will not go into the details here. It's kind of bounded rationality with more practical approach, such as, for example, how do I bound the computations? For example, many people, and for this reason, good enough behavior is under this, many people actually have this indifference between sums. So suppose I offer you 1 million or 1 million plus 2. You would be indifferent between those sums. Who cares about those two? Even 1 million plus 1,000 compared to 1 million, who cares about this small difference? But if I just offer this 1,000, it's a lot. So same, 0 and 1,000, you would definitely prefer the 1,000, but 1 million and 1 million and 1,000, which is the same difference, it would be indifferent. So this known behavior of people is actually accounted for in the good enough behavior. And some other aspects of this type are taken into account, reducing further, but very practically, the space of possibilities. Okay, so far it was much about preliminaries to get into the basic understanding of aspects we are going to look at. I'm going to look into stability and equilibrium briefly, because eventually one of the things that we want to have when we have a game or a protocol is that it would arrive at a stable point where players or people or agents are not motivated to change the current situation. For many reasons, but they're not interested in changing it. So, in fact, we need to evaluate the protocol in many ways. One of them would be payoff maximization, as discussed before. Another would be Pareto optimality. Some of you may be familiar with this, but if not, suppose we have some profits to be made in a protocol or in a game. Suppose the maximum that we can make is 100. We want this maximum to be fully utilized. So suppose there is some distribution of the payoff among the players. You want all of the 100 to be distributed. You don't want some sums to be wasted. So a Pareto optimal distribution would be such that it would actually utilize all of the resources. So if you have 100 which is divided, so if you want to take some of you back to the system or to society, this sum which was taken from you should get to someone else, to you, for example. And the statement says there is nothing which is, you cannot improve for some player and not hurt another player. This is a Pareto optimal case, okay? And so, of course, we would prefer solutions or games to be such that be Pareto optimal. This is a clear preference. Otherwise, something is wasted, okay? Now, of course, we would like it to be stable as well. Now, stability is nothing which is, there's no single stability type. There are many ways to measure stability, but in general, just to get a flavor, it's a case where players are not motivated to change the result at which they arrive at. They're not motivated because they will not do any better, okay? How do we arrive at stability? The easiest case is where we have dominant strategies. Strategy is dominant if once you take it, whatever others do, it doesn't matter what others do, for you it's the best possible you can do. So of course, if there is a strategy which is dominant and you adopt it, you are in the best situation you can be. So if there is such a strategy, I'll try to compute it and let my agents or players adopt such a strategy. Unfortunately, in most cases you don't have such a strategy. So there's no strategy which is dominant in many cases. So John Nash has identified this and actually came up with the Nash equilibrium, which is again based on strategies, but in such a case, the motivation of staying at following some strategy is based on the fact that you assume that others are in their best strategy, and unless they move from their strategy, for you it would not be beneficial to move from your strategy. We'll look at an example shortly. In some cases, you don't have a Nash equilibrium. So there's no such strategy that would be such that you can stick to it and get your maximum given that the others did not move from theirs. So you have a mixed Nash where you actually apply probabilities to your strategies. We'll go into the details of that shortly. And you also have some cases where you don't want to rely only on utility. You also want to have types of the players, of the agents. Usually type is associated with history, with other types of behaviors and so on. We would not go into the details of the base Nash case, which attaches types to agents, but the details are in the literature and they are based basically on Nash with extension. Have you seen that before? I would assume that. If you have not, anyway, just briefly speaking, the prisoner's dilemma is such that you have two prisoners, or actually people accused of some crime. They can either cooperate with one another or defect. One of them can defect, or both of them can defect. So cooperation in this case means that they do not tell about the other guy. They don't tell the police or the authorities about the other guy. Defection means that they actually tell about the other guy, but saying that the other guy did the crime, maybe I have participated as well, but that's the basic. They have two strategies, either cooperate or defect. If both of them cooperate, so they actually get free, because so that in this table, cooperate means that they get some gain, 2 to player 1 and 2 to player 2. But if player 1 cooperates, what's this? We have player 1, if player 1 cooperates and player 2 defects, so this is the place. So player 1 would get -2 because the guy would be punished severely. He didn't say anything. He actually said he didn't do the crime, but the other told him that the guy did do it. And so the other guy would get a prize for telling about so number 2 will get a prize of 4, and number 1 will get -2, will get imprisoned. Symmetrically, if number 2 cooperates and number 2 defects, number 1 would get a prize of 4, and number 2 would be punished severely, -2. And if both of them defect, each one of them tells about the other, would both get imprisoned, but not as severely because actually they helped the process of investigation, and therefore their punishment is not as severe. The stable case here is this. Although clearly it would have been better for them to cooperate, because then they would get for free, but this is the stable case, and we can show this by showing that if they know, both of them know that, so suppose they cooperate and cooperate. In such a case, if number 2 cooperates and number 1 knows about it, so between this guy, number 1 can get either 2 or 4 when this guy cooperates. Getting either 2 or 4, there's a clear preference for 4 over 2. So in case that number 2 cooperates, number 1 should definitely defect, because defection would give much more benefit. Now, but if this guy defects and number 2 knows about this, so number 2 can choose between -2 and -1. Okay? So in case number 1 defects, number 2 should definitely defect because it's better to get -1 than to get -2. So clearly, if this guy defects, this guy should also defect. You can do the same math from this direction as well. So this is the only stable point. Okay? So this is a Nash equilibrium, a classical Nash equilibrium, that shows you that Nash does not necessarily mean that the best possible payoff here, but it's the best possible given the behavior of the other. Okay? So we have a Nash case here. Okay, now it's your turn. You are sitting and relaxing, now it's your turn to do something. So, pair up. You can do triplets as well, but let's see. You're seated kind of pairs or triplets. We have this game. Let's see if you're cooperative or not. We have this game. So there's some sum of money. Suppose it's 4. You can either share or split. Either split, share. Sorry, you can either split, share. Actually, take this 4 and divide the 2, and each one gets 2. Or still, try to take the whole 4. But if both of you are taking the whole 4, or trying to, you actually get punished. You don't get the whole sum. You get just half. You get just 1 for each, not 2 for each. Now, all you need to do is to write on a note, without others seeing, what you are going to do. Split or steal. Would you write on a note? I'll collect them. Don't show.
Individually or in pairs or triplets?
We can do it. We can actually do it for the whole class and see what the statistics are saying. Would you I'll collect this piece of paper with steal or split? Don't tell the other guy.